Have a look at these pictures. I tried to reproduce famous drawings of humans and rabbits' embryos drawn by Ernst Haeckel. Can you tell for sure which one is human and which one is a rabbit? Probably no. I wouldn't, if it was not me who drew the pictures. Why they're so similar? And how can such different organisms like humans and rabbits developed from a nearly identical embryo? Think of it. These are limbs, humans and horses. They are different for sure, and they serve different purposes. Human arms are good for grasping, and horses' forelimbs are built for speed. But the blueprint is surprisingly similar. And even whale's limb exhibits this similarity. Why they are so similar? How such a different limbs with different purposes may be so similar? Think of it. And we are not the first ones to think about this. People tried to understand how life developed, how living organisms related to each other since ancient times. The ideas of the past were naive but confident. Humans were always at the top of the world, or more precisely, at the top of the ladder. This idea is simple. You put inorganic matter in the bottom of the ladder, the human being is at the top of the ladder, and all other organisms are distributed based on a simple principle. The less something resembles a human, the more primitive it is considered. Another ladder-like concept is that life strives towards some perfection and some ideal type of creature. And unsurprisingly, often this perfection was considered to be human. One of the most famous proponents of this ladder-like concept was Lamarck. Look at him on the left. But his ideas were defeated, were overturned by the guy on the right. You've probably heard of him, Darwin. Darwin proposed a brilliant idea that development of life on the earth is not a ladder, it is a tree. Starting from a single common ancestor, organisms accumulate small differences until they can't mate. At this point, they become the common ancestor to their lineages, and the process continues. And if we draw this process, it will resemble a tree. This idea is very powerful. And modern concepts of evolution in core are still based on Darwin's suggestion. But there are still people who doubt their evolution. They say that evolution is too slow to observe. We can't tell for sure that this is real. But what if I tell you that we can witness evolution, that we can see it unfolded in real time? In 1988, a biologist, Richard Lenski, set up an experiment that showed us the evolution. What he did? He took 12 populations of Escherichia coli bacteria and simply let them grow. No interventions, no forced mutations, just bacteria competing for survival. And during the experiment, which lasts for many years and allowed us to show over 70,000 generations of bacteria, the scientists took samples of bacteria and preserved them for the future analysis. And sometimes bacteria had some distinct changes. DNA is an instruction manual for how bacteria look like and behave. And if we can compare the DNA from the start of the experiment with the DNA of the later time points, we can find the exact mutations that are responsible for the changes. And over these 75,000 generations of the bacteria, something really changed. And let me tell you about this in more detail. Bacteria, Escherichia coli, lives in a liquid. And in this liquid, nutrients are dissolved. Bacteria uses these nutrients for growth and reproduction, just like we use our breakfasts and dinners to live. Aside from the nutrients, there is a chemical called citrate in the solution. It is technical chemical that is used to stabilize the solution. And normally, bacteria can't use it for food. The scientists noticed that one of the lineages apparently started to grow much faster than the others. And tests shown that these bacteria developed an ability to use citrate as a food. But how did the bacteria develop this ability? Did they purposely try to develop it? Not really. It was due to some random mutations. Let me explain. Normally, DNA constantly changes, constantly mutates, just because life is not perfect. Most of the mutations are neutral. They don't change anything. Some of them are harmful. They can be fatal. But once in a while, a lucky mutation appears, and it gives the bacteria some trait that is beneficial to it. And this is what happened. The mutation that led to the development of trait of eating citrate appeared in the bacteria living in a liquid full of citrate. Perfect timing. And now this bacteria has an advantage. And in evolution, advantage means reproducing more than the others. So this bacteria was able to use citrate for food. They reproduced better and outcompeted the old strain. But evolutionary research has implications beyond the lab too. Knowing the evolution of bacteria helps us understand antibiotic resistance. Knowing of the principles of evolution helps us know how diseases emerge and how we might control them. For example, updating of the annual flu vaccine is based on the knowledge of viral evolution. Flu is caused by a virus that mutates rapidly. That means that there are actually many viruses circulating in the world. But one of the strains is usually dominating. And this dominating strain changes from year to year. So if we use vaccine from last year's, it might not be effective to the new dominating strain. It is like fitting into a pair of jeans that you wore in high school. By comparing the viruses from the past years to the current ones, the scientists can predict which strain will be dominating next year and develop an effective vaccine. Life's ability to change and adapt is one of its greatest strengths. And if we can predict those changes, we gain the power to harness them. Evolution isn't a concept from textbooks. It's a dynamic force that shapes our living world. And if we uncover its mechanisms, we unlock the secrets of life itself. Evolution isn't a concept. Evolution is life. But let me go back to the Lenski experiment for a moment. Lenski's experiment wasn't meant to cure disease. It wasn't designed to revolutionize technology. It was an attempt, a humble attempt, to understand how life evolves. And from that curiosity-driven research, we gain results that go far beyond the bacteria. Fundamental research is the foundation of progress. The discoveries that shape our world now, DNA, antibiotics, vaccines, began with the scientists asking questions without knowing where the answers would lead. If we focus only on what's useful right now, we'd miss the breakthroughs that changes everything. Because sometimes the most powerful ideas start with pure, aimless, courageous curiosity. And tomorrow's solutions often starts with today's questions. Thank you.